Hello, good afternoon, everybody. My name is Nassar, and I'm from University of Glasgow, Bendable Electronics and Sensing Technologies Group. Today I would like to present to you our work on 3D printed interconnects on bendable substrates for 3D circuits. I'll start by giving you a bit of a background on the technology itself and how it can be used for this purpose. I'll walk you through the fabrication method, which we've decided to take. I'll talk a bit about the structure and the material formulation. Our interconnect performance, I'll give you a bit of a glimpse in that, and I will conclude the work and give you our outlook on the future work for this technology. You can start by asking a question of why 3D printing, specifically why 3D printing for circuits. And we can talk about 3D printing in terms of technology that's been around for 30, 40 years, but probably its boom has happened in the last decade or so. It provides a lot of design flexibility and prompt design changes. But not only that, there's the mass customization that we're also really interested in. Because in the terms of fields of biomedical field or in terms of wearables, we can use 3D printing to our advantage to be able to mass customize whatever products we have. In terms of materials, 3D printing has generally been associated with polymers and metals. However, now you can look at a bunch of different materials that can be printed using 3D printing, and we are hoping to exploit that possibility into many avenues. On top of that, in terms of from a fabrication point of view, 3D printing can provide us with automated fabrication with multiple materials simultaneously to provide to help us achieve our goals. In terms of 3D printed circuits and systems, the primary goal is that we can efficiently use the 3D space available within the structures. Particularly also as well is that we can form complex geometries that we can't really attain using traditional fabrication techniques. Particularly we're thinking about printing in an out of plane. Particularly one of the pictures is the work which we presented in terms of an embedded sensor with printed passive components. And this is really interesting, particularly if you look at the long term and particularly if you look at customization and the way we can alter the shape and alter the different circuits within the shape. But then we can also start to think about bendability and bendable materials in terms of substrates and conductive materials as well. I'll go through a bit of multi-material 3D printing, and in terms of this, it's quite difficult to integrate some of the established 3D printing techniques such as stereolithography, laser sintering, or binder jetting. Usually it's quite difficult to introduce multi-material 3D printing in those systems. But not only that, they're quite difficult to set up and customize to your own specific use. They're also at a much higher cost than other types of 3D printers. So if we're looking at fused deposition modeling and liquid deposition modeling, we can really use the fact that they are open source, readily available, customizable, and low cost to suit our advantage. But obviously the main point is that we can still print multiple materials at the same time. In terms of the liquid deposition modeling, we're chosen to go for a direct ink write method instead of pneumatic systems. Although pneumatic systems, you might argue, that can provide a little bit of better precision. However, with the bulky air supply units, it's probably not as readily available as direct write ink methods and not really as readily distributable. As well as in the terms of the extrusion mechanism, a key element to consider is retraction of the conductive inks in the printing, because one thing you want to avoid when printing tracks or interconnects is some cross linkages between the printed tracks. So in terms of multi-material 3D printing, we've gone for FDM in terms of printing the substrate, but not only that, printing as well some conductive materials as well, conductive solids, and adding a paste extrusion mechanism for the multi-material 3D printing. Things to consider are our feature size and the curing process and the materials, which I'll talk about in a minute. In terms of the printer customization in our lab, we've integrated a readily available desktop 3D printer, the RepRap, and added the Discovery paste extrusion system to that. One really strong advantage of the Discovery paste extruder system, or this type of system, is that it's not directly placed on the X carriage of the 3D printer. By not placing it there, we are avoiding added vibrations to the printing setup while printing, which may cause some discontinuity within the prints, especially with a large system and a large extrusion mechanism if we're looking at a large amount of material. But not only that, in case of a large weight on the X carriage, they might cause a misalignment between the printing X carriage and the bed level as well. The paste flow itself goes through the syringe and through a Bowden tube, and through that, through a Lure lock connector and through a nozzle. The particular nozzle we chose is 0.4 millimeters. However, also another advantage of this is that the nozzle diameter is easily changed by changing the nozzle itself. In terms of paste flow, we can look at different properties. And specifically, with the specific properties of the paste itself, we can alter the velocity in which it's printed, and in turn, the feature size which we can get, and the repeatability of the prints. Particularly, we look at the density of the inks, the viscosity, surface tension, and the droplet diameter as well. Eventually, we're interested in the velocity of printing. We're interested in the parameters of printing instead of in terms of the feed rate of the extruder mechanism, to be able to get the most reliable and repeatable results in terms of this printing mechanism. Now, in terms of materials, packaging materials, there are many. Not many are bendable. One of them, a really good one, is TPU material, commercially known as NinjaFlex. It's bendable enough to allow for repeatable movement, and it allows for wearable applications and to follow reversible deformation. To this extent, it's quite useful to our eventual goals. But not only that, it also shows good adhesion to inks and other solids. So in terms of printing thermoplastics, we're looking at a holistic system of 3D printed circuits. We're looking at some bendable parts and some non-bendable parts. So with regards to PLA and ABS, NinjaFlex binds well, as well as binding with inks. Another important thing to note is that with such rubbery materials or bendable materials, it's important to print at a much lower speed to avoid any warping of the material itself during the printing mechanism. Now, to look at the conductive interconnects for our 3D circuits, or particularly our bendable 3D circuits, we're looking at inks, but as well as conductive filaments as well. And one conductive filament which we went for is commercially known as electrify conductive filament, is based on copper fillers and a biodegradable polyester. Now, this was reported to have quite low resistivity, and even one study showed its bendability for around 500 cycles. So we thought it would be a good place to start in terms of this type of material study. Now, in terms of the paste, which probably might be a bit more interesting because we can tweak it quite a lot more, although we can tweak the fillers in the thermoplastics as well. But in terms of the ink, if you see some examples of 3D printed circuits, a lot of them are planar, first of all, but not only that, a lot of them use silver ink. And silver ink is quite expensive, but not only that, commercial inks don't allow us to alter the properties in terms of viscosity and the specific properties which we need for repeatable printability. So we've used an in-house formulated graphite-based conductive ink. Primarily components of graphite powder and isopropyl alcohol as a solvent, which we've experienced gives us some good printability. We've added a dispersant as well, Triton X100, for better dispersion of the powder. But we've also added a binder of ethyl cellulose to better bind the conductive particles together during printing. The mixture is obviously still stirred continuously to get homogeneous ink to be able to allow the printing, or to be able to allow the dispersion of the graphite powder. Now, the printed bendable structures themselves, like I said, 3D printing in terms of 3D printing circuits is relatively new field, and the work done so far has been done on planar circuits. So in terms of bendable circuits as interconnects, this is a kind of our initial outlook on that, and we're quite excited to delve deeper. These are some images of some of the printed tracks on the bendable substrate. On a radius of curvature of 27 millimeters, it shows a kind of qualitative view of the bendability of these materials. In terms of going a bit deeper and looking at what's actually happening on the surface level of the substrate as well as the conductive materials themselves, we also haven't come across any research that looks at these types of materials in this use, as well as the use as bendable interconnects. So we're looking at the optical microscope images, and in A, we look at the flexible substrate itself, the TPU. In B, we look at the electrify on the NinjaFlex, and on C, we look at the graphite IPA conductive ink on the NinjaFlex itself. And as you can see, obviously, I mean, it's clear to see for any material people around here that there are some cracks in the system itself. A lot of this can happen either through printing, and through the bending as well. And this is one thing in moving forward, is to try and avoid and try and optimize. And like I said, in terms of binders for the ink, this can be hopefully taken forward. And in terms of tweaking the printing mechanism for FDM printers, the cracks for the electrified filament can also be solved. For some resistivity measurements, to get an idea of the resistivity of these materials, the electrified filament, as we found, showed a much higher resistivity than commercially stated, or even stated in another piece of research. So this was quite, I'll say, alarming to us, because we wanted a kind of repeatable process. But then it also kind of maybe opens our eyes and eyes of the field in terms of producing filaments that can suit a variety of different printers, but also in terms of the properties of printing itself, for example, the printing temperature or the printing speed, etc. The graphite ink itself shows a much lower resistivity than the filament. However, it's still, I think, quite high in terms of high-performance connectors for 3D circuits. And in that, I think it's clear it's not a very comprehensive study. However, with the fact that this area has not really been explored before in terms of bendable interconnects for 3D circuits, we're quite excited to look at this levels, particularly with the optical measurements of these materials. And to conclude the talk, I presented to you our work on a multi-material 3D printing system, including both FDM and LDM printing, fused deposition modeling and liquid deposition modeling, to provide an automated, low-cost fabrication technique to produce bendable interconnects on bendable substrates. And from that, we can look at a material study of this and its use in 3D circuits, as well as future applications for wearables. And for sure, our future outlook will look at exploring different materials, different parameters, tweaking with the different properties of the materials themselves. But further on, we'd like to look at out-of-plane circuitry, but as well as bendable materials, high-performance bendable interconnects with moving parts in the biomedical industry for things such as prosthetics and wearables. And with that, I thank you very much for your attention.